So today we have Dr. Kevin Heng here to tell us about atmospheric retrieval of exoplanets. We heard a little bit this morning about an ultra-hot Jupiter exoplanet with lots of weird properties. This talk will be a broader overview of exoplanet abundances and extracting them from their spectra. Kevin is the director of the Center for Space and Habitability at the University of Bern, where he's been since 2013. Prior to that, he got his PhD at the University of Colorado in Boulder, spent some time at the Institute for Advanced Study at Princeton, and then also was a Zucchi Prize Fellow at Zurich before moving to Bern. And so, yeah, it's my pleasure to have you here today. I've had some great conversations with Kevin. I hope you have too. And so I look forward to your talk.
So thank you very much, and thank you for giving me 1 hour of your life, and I will try to make it interesting for all of you. So before I came to Carnegie, which I've never been, I looked at the website and looked at all of your research interests as much as I could, and I noticed that they were very far away from what I'm going to talk about. So if something is not clear, you should feel free to interrupt me during the talk, regardless of the video recording.
Yeah, that's
it's a specialty.
Right. So I would like to talk to you about a problem that, first of all, I have a very big group. So I have, in fact, not all of the postdocs are listed. I just hired a 7th postdoc in my group, and I have 4 PhD students. So we work on a wide variety of things. In my group, we look at 3D general circulation models that were used to understand the climate of Earth. We do high temperature atmospheric chemistry. We do a lot of radiative transfer, which is very close to my heart, which is distinct from the inverse method that I will talk to you about in this talk. And recently, I got very interested in geochemical cycles on rocky exoplanets, because if you want to talk about if you want to talk in any meaningful way about atmospheres on rocky exoplanets, you have to understand secondary atmospheres. So there are lots of things to talk about, and I can't cover it all in one talk. So I made the choice to focus on just 1 out of the 6 or 7 things that we do in my group. And I'll give you a flavor of the last component of my group, which is machine learning, and how it's related to all that. So I would like to give you a few slides of introduction. So I would say that it's fair to say that exoplanet science is in a slow but steady evolution towards just stamp collecting, detecting these things and saying what the masses and radii are, and whether they're Neptunes or Jupiter or super Earths and whatnot, to what most of us would call characterization, a word that means many things to many people. But to people who are interested in atmospheres, that's what it means. And you see this slow drift from detection to characterization also in the missions of ESA and NASA. So you can see the drift from Kepler to TESS and CHAOPS, which is a mission that is led in Switzerland and in Bern, towards missions like Ariel, and Webb has undergone some adjustments so that it can do transit spectroscopy of exoplanets. But what is really interesting is that NASA is currently conducting 4 mission studies of the successor to these observatories. And it's really curious that 3 out of the 4 focus on habitable exoplanets, whatever habitable actually means. Right? And there's also the next generation of really large ELTs, where if you read the white papers or the red books or whatever you call these things, you'll see that there's a keen interest on atmospheres of exoplanets and habitable exoplanets as well. So we're heading down that path. This is every exoplanet scientist's dream, that there's some kind of a dreamscape, like a TRAPPIST-1 planet that we can fly to and send a rover and collect samples and do mass spectrometry and so on. And I say this because I'm an astrophysicist and an atmospheric scientist who is employed in the planetary science department, which has geologists. And for many of my colleagues, if you can't do that, the talk stops here. So there's no point in going further. And that's fine. That's one way to do science. The reality is going to look like that. So the reality is going to look like you measure some spectrum with bumps and wiggles, and this is actually a real spectrum of Earth. I'm not going to spend any time describing how these guys measure this spectrum. If you're interested, look at this paper. But you're going to measure some spectrum, either emission or transmission spectrum. You're going to work very hard and interpret what these features are due to, which molecules. And to accomplish that, you need to solve the inverse problem, right? You need to go from the measured spectrum to chemical abundances and atmospheric properties and whatnot. And and one of the things I hope you will take away from this talk is that it's relatively easy to say what is in the spectrum. Is it water? Is it CO? Is it CO2? It's much harder to say how much of each is in the spectrum. So today I'm just going to focus on transmission spectra and not emission spectra. This happens when the planet goes in front of the star. And if you look at the planet and its atmospheres at different wavelengths, you will notice slightly different projected sizes. And this is because imagine if you had a planet with an atmosphere that only had water. At certain wavelengths, water is transparent to radiation. And therefore, the size will look slightly smaller. And at other wavelengths, it is opaque to radiation, so the size is slightly bigger. This is a small effect. It's a part in 1,000 or less. And if you can measure these differences in transit depths, then there's a mapping between the cross-section of the atom or molecule you're interested in and the transmission spectrum of the exoplanet. But this is a tricky business, which is the point of this talk. But before I go there, I should point out that if you're interested in transmission spectra, there are two very important historical papers that one should read. One of the most important papers is a 2000 paper by Sarah Seeger and Dimitar Saselov. And in this paper, they did a few things, including predicting that the sodium doublet would be observable in transmission spectra. This was confirmed just 2 years later by Dave Charbonneau at Harvard. And they also predicted that the meta-stable helium lines would be also seen in transmission. This took 18 years to confirm, so this was only measured last year. There's a very underrated paper by Tim Brown written in 2001, where this is an interesting paper because the paper has almost no equations. It reads like an essay, but he describes essentially all of the ideas that we are formalizing and working on right now in the theory of exoplanet atmospheres. So I very much recommend this paper if you would like to get an overview of transmission spectra. So I would like to start talking about transmission spectra with order of magnitude. So this is the planet that you're observing at some wavelength. And here's a telescope, and you measure the transit radius, right? And you would like to know what's the typical length scale of this transit chord. And in the order of magnitude sense, you know that there are two length scales in the problem. One is the radius of the planet, and the other is the so-called pressure scale height. It's the typical height or length at which the pressure varies at an order of magnitude level in an atmosphere. And typically, the pressure scale height is much smaller than the radius, like about 1%. So what happens when you have two quantities where one is much smaller than the other, you want to take the average. It's not the common sense mean, which is h plus r over 2. That's the arithmetic mean. It's the geometric mean, right? So you take the geometric mean of these two quantities, and that's your length scale. If you do it more carefully, which is the subject of this paper, you get an extra square root of 2 pi and all of the dependencies correctly. I forgot to say that this is the number density, the cross-section, the length. So you get the optical depth. Now that you know this length scale, let's put it all in a triangle, right? So let's put this all in a triangle. This is the radius and a little bit, and this is the length scale we just talked about. And now if you solve for this little bit, you will get that this little bit is pi over 4 multiplied by the pressure scale height, which is roughly the pressure scale height. Why is this interesting? It's because in an atmosphere in which pressure balances gravity, hydrostatic equilibrium, to go a factor of 10 up greater or less than the pressure you're at, you need to move 2.3 pressure scale heights. So the fact that the pressure scale, this length is below 2.3, and in fact only roughly about pressure scale height, suggests that the transit chord, despite the way it's drawn, is nearly isobaric. So you're nearly probing the same pressure across the transit chord. So let me prove this to you. So here's calculations done by one of my postdocs, Daniel Kitzman. This is the transit depth, and this range of wavelengths is chosen to mimic the WFC3 instrument on the Hubble Space Telescope. And the WFC3 is centered around a family of water lines at 1.4 microns. And the purple curve is a calculation where this isobaric approximation is not made. And the other curves, the blue, red, and yellow curves, are using an analytical formula that I will talk about shortly, where one has to choose some isobaric, some constant pressure. So these are 3 arbitrary choices. And you can tell that for all intents and purposes, well below the noise floor of Hubble, this formula is exact. So this implies a few things. First, that you are insensitive to pressure variation in transit. You are also insensitive to pressure, so it doesn't seem to matter what pressure I take. And one can understand this from a physical point of view, which is that when the temperature is sufficiently high, this is about 1,000 Kelvin, the cross-section of the water molecules are dominated by the peaks of the line and not the wings of the line. And it's the wings of the line that contain the pressure information through pressure broadening. So if you're only dominated by the peaks, you're blind to pressure. You need to go to very low temperatures to be sensitive to pressure. And because you are blind to pressure and you're probing such a narrow range in pressure, it means that it's extremely challenging to probe any kind of temperature variations. It means that you're roughly isothermal as well. So the good news about transmission spectra is that it's simple. The bad news is also that it's simple, right? You don't actually say that much. You're blind to a few things. And this will come out later when we talk about analyzing real spectra from the WFC3. So I would like to introduce you to atmospheric retrieval. Some of you probably know this paper better than me. This was written by a cosmologist, Roberto Trotta. And I call this procedure models with error bars, informally. So you have some data, in my case, a transmission spectrum, and you need some kind of model, a forward model that translates between the opacities, which are cross-sections per unit mass, and some assumption about chemistry or lack of, into a synthetic spectrum. You need to think hard about what the prior distributions of these parameters actually are. You then put it in what I call a sampler or minimizer, and you would like to find the best fit solution in a multi-dimensional parameter space. You could either use a Markov chain Monte Carlo procedure, or you could use something called nested sampling, which Trotta talks about. So I must admit that nested sampling is something that we use as a gray box. We don't question it very, very much. The rest of the ingredients we question in exquisite detail. But the one advantage of nested sampling, which I will show in practice later, is that it allows you to do something called model selection. It allows you to essentially apply Occam's razor. It answers the question, given the quality or lack of the data, what's the correct level of sophistication or model that I can apply to do the interpretation? And of course, you get the posterior distributions of parameters. So this is the overview of how atmospheric retrieval works and is. And I'll show you in practice how it looks like when you...
Where are the error bars in all of this?
The error...
Since you said models with error bars, at what stage are you quoting the errors?
Well, if you would...
Data or from this model selection?
The posteriors.
Sure. But what is it that generates those?
Well, you're sampling the data with some uncertainty on each data point, and then this results in not getting a single number for each parameter, but a distribution of numbers.
Right, but don't the models generate some uncertainty as well?
I don't understand.
Model
Those.
selection. You have a lot of models.
You're saying, how do I select between the models?
Well, how do they interface with the posterior distributions?
So each of the models will be associated with a Bayesian evidence. And then if you look at ratios of these, then this allows you to select one model over the other or not. Does that answer your question? Not quite. So this is the procedure, and I also find it useful to think about atmospheric retrieval in 3 different physical regimes, and it's also useful to associate it with roughly with different observatories. So for HST data, using the WFC3, which I will show you in detail, I would consider it low resolution and moderate wavelength coverage. You don't resolve the lines at all, but you resolve the shapes of line complexes. For James Webb, whenever it flies, you don't quite resolve the lines as well. You get better resolution on the shapes of complexes, but you get a lot of leverage from the spectral continuum because of the very broad wavelength coverage. But one very interesting range, which I talked about this morning, and I will show you a little bit later, is data coming from the high-resolution spectrographs on the ground using first the VLT and the next generation ELTs, which is you get very high resolution, you get narrow or moderate wavelength coverage depending on the instrument and the mode you're using. You resolve the individual spectral lines, but what you give up is that the spectra actually doesn't have an empirical normalization. And there are a few other things that come together, which I'll talk about, and it's not clear what you get in the end. I'll talk about this as we go along. So I would like to devote about a quarter of the talk to an issue that has been a little bit controversial. I call it the normalization degeneracy. This was discovered numerically in this 2012 paper, and then later talked about in this 2014 paper, also numerically. So this is a transmission spectra. Again, this is the wavelength of WFC3, and this is some data set or some object. It's not important. What's important is that is the size of the error bars compared to the spread in the models. So what Caitlin Griffith has done is that she has calculated 4 models, and it turns out that the models need a normalization. And she has chosen 3 normalizations in which she just varies the digit in the second decimal place. And she finds that this small variation in the normalization, in the transit radius normalization, corresponds to 5 orders of magnitude in the water abundance. And this variation is well below the uncertainty on each of the data points. So this is a problem, because it means that if you don't understand this well enough, you couldn't even say what the abundances are at the order of magnitude level.
Sorry, so the water abundances are what's retrieved, or their input? I'm a little confused as to what the water abundance is.
There's no retrieval being done here. She's just calculating some models. She's not doing any inverse problem. And she's just trying to show that models with very different water abundances give more or less the same transmission spectra. That's all she's trying to show in this figure.
Okay.
But the normalization in this case is really just the height of those curves.
That's correct. I'll show you this in the next slide. So this was discovered numerically in these papers, but no explanation was really given. So we thought about it in 2017, and we could explain it in terms of a very simple analytical formula. So this is the formula that was validated in a few slides ago that I showed you. And so it fits your intuition in the sense that the transit radius at some wavelength is some normalization, and a bunch of stuff that's a factor of a few, multiplied by the pressure scale height. So this tells you in terms of physics that spectral features due to lines are a few scale heights tall. This reference radius comes from the fact that when you derive this analytical formula, you need to integrate from some reference to whatever you're seeing. So it's a constant of integration. And along with the reference radius is a reference pressure that's being tied to this reference radius, which I'll come back to. So the other quantities are not terribly interesting. This is some universal constant. This is the gravity of the planet. And the opacity is a combination of, which is the cross-section per unit mass, is a combination of the relative abundances of the molecules and the cross-sections. So what is really interesting is the relationship between these 3 quantities. So you have the reference radius, some reference pressure, which you have no way of knowing in a model-independent way, and the opacity, which contains the actual quantity that's interesting to you, which is the chemical abundance. And you can see just analytically that if you make a really small change in the reference radius, it needs to be compensated by a very large change in either of these quantities because it's hidden in the log. And this explains the behavior you saw in the earlier plot from the other paper in 2014. So there's a 3-way degeneracy that is related to the normalization of the transmission spectrum. And you can specify this from first principles because you do not know what the relationship between these 2 quantities are from first principles. Right, so this raises the question.
Also, wait, sorry, just to get it straight. You're already starting at a disadvantage because H is probably of order of 10 to 1% of R naught, right?
That's right.
Okay, so the lever in front of the whole pre-factor is also killing you.
That's right. That too. Go ahead.
I guess another thing implicit in this is that the wavelength dependence of the opacity is fairly broad, because if it was more narrow, you'd maybe be able to isolate these effects.
It's the other way around. You isolate it by being broad. I'll show you.
Okay.
I'll show you tests that demonstrate this.
But the reference radius is tied down by the eclipse, the transit, right? The shape of the transit.
Sure.
I realize there's error associated with that, but is that the same kind of error as the pressure where you really don't know at all what I mean, they're sort of very different things. So you have no other information on the pressure, do you?
You don't, and I'll show you in a moment how you can get some information. But let's put it in a practical sense, right? Imagine I have a planet that is 1.1 Jupiter radii, and then I'll ask you the question: so what's the pressure at 1.05? And the answer is I don't know, right? I can't give you the answer in a model-independent way. I just cannot, because it requires that I know the structure of the planet, which I don't from first principles. So this seems like a really severe problem, but I'll show you that there is a solution to this problem.
By the way, see how good we are at
No, it's fine. I was brought up academically at the IAS where there was a speaker being stopped on the second slide for 45 minutes. So this is nothing. This is nothing.
Yeah, I know, you're right. You get away with it pretty easy.
So the key question you want to ask is that, do transmission spectra encode enough information to break the normalization degeneracy? You want to ask that question, because otherwise, if you can't answer that question, there's no point in going on, right? So to understand this question, we do some mock retrievals where we know what the ground truth is. So here's a mock spectrum under rather idealized conditions with small error bars in WFC3. And this is a very simple model. It only has two parameters, physical parameters. It has a temperature. It only has water, so it only has a water abundance. And it has some normalization to P0 that we put in. We assumed it. And the real answer is this. And if you knew what the real answer was, this would be your posterior distribution on the water abundance, right? The dark shaded posterior. But because you do not know what, and you try to retrieve for it, you get something that is unconstrained and prior dominated. And this results in this fat posterior, which is bounded on both sides by very different things. It's bounded on the right side by physics. It's bounded by the fact that if you become too water-rich, your mean molecular weight becomes too high, and your scale height becomes too small. It means you need many scale heights to describe a spectral feature. So that rules it out, right? So at some point, this doesn't work because you run out of scale heights to describe this feature. That's easy to understand. The left side is very insidious because the left side is bounded by the fact that you have assumed the right side of this prior on the P0. And what is annoying about it is the fact that this range, this normalization degeneracy, determines the width of the posterior, with the left side being prior dominated. The reason why you can still retrieve the temperature is because you can think of these as different modes in the spectrum. The temperature has an exponential influence on the cross-sections, so it behaves like a stretch factor. The influence of the water abundance on the cross-section on the transmission spectrum is more linear, so it's more like a translation mode, like a local translation mode. And the P0, the reference pressure, behaves like a global translation mode. So what happens when you add clouds to it? So now this is cloud-free, just water. Now let's add gray clouds to it. Oh, sorry. I already said all this. So now if you add clouds to it, now you have another degeneracy. You have a second degeneracy that's caused by the fact that if you want your spectral features to be stronger, you increase the amount of water in the atmosphere. But this can be negated by making things cloudier, which brings the strength of the spectral feature down. So now there's a cloudiness abundance degeneracy in addition to the normalization degeneracy. And collectively, this determines the width of your posteriors, of the water abundance.
So is the cloud just a gray opacity that you put on top of everything?
Yes, it's the simplest assumption. It's the gray opacity. In our actual retrievals, we put in non-gray clouds, but just for the sake of argument, I put in a gray cloud so that it's clean. The next thing you could do is you could put in more molecules, because for physical reasons, we expect hydrogen cyanide and ammonia to have spectral features in this range of wavelengths and this range of temperatures. And here you see clearly that each of them is limited by the normalization degeneracy, because this is unconstrained and prior dominated. It's also limited by the cloudiness abundance degeneracy, which determines all of the widths of these features. But again, for reasons I just described, the temperature is rather tightly constrained. Right, so this is for HST-like Mach spectrum. What happens when you have a JWST-like Mach spectrum? So this answers your question, which is that now if I keep the wavelength range fixed, but I populate it with more data points, then what these extra data points are doing is that it's giving me much more information on the shape of the spectrum. And so effectively what this does is that it converts these abundances into local translation modes that are well constrained. And this becomes a purely global translation. This is a stretch factor, so they become more or less orthogonal modes, if you will, in the system. And now you can see that the normalization degeneracy is gone. Right? There's no longer a streak. And the cloudiness degeneracy, at least for a gray cloud, is also gone. So the hope is that when you have data of this quality, that you can actually have enough information in the spectrum to solve for the normalization and not be prior dominated by the right side of this reference pressure.
The scatter in that plot is mostly real, or is it a function of wavelength itself?
The scatter in this plot comes from the fact that you have a rich array of waterlines, which doesn't show up here. But if you look at my computer, maybe the other plots. Yeah, you can kind of see it here. You can.
So that underlying spectrum is
Yes.
has the signal noise.
The underlying spectrum is a spectrum with no noise. And if you bin it in specific bins, you are capturing the fact that the richness of the spectrum in a partial way. So the answer to that question, this question which I asked is, do you have enough information to break this degeneracy? For HST, kind of. And for James Webb, we hope the answer is yes.
So there have been several planets that have had abundances derived from HST spectroscopy. Don't believe those?
Yeah, this caused a lot of controversy because when we wrote that paper, we pointed out that many of these papers, if you read them carefully, there's a section that says, they essentially say we assume the reference pressure to be the white light radius, and we would just simply assume the reference radius to be the white light radius, and we assume the reference pressure to be 10 bars. And I can show you a list of 30 papers that make this assumption. So I would say I wouldn't believe any of the abundances in these papers.
But did they implicitly know that that was a bad thing to do?
It's hard to tell.
The only thing that they could do.
It's hard to tell. I think many people have not noticed numerically that there's a freedom to adjusting your transmission spectrum up and down, but no one seemed very bothered by it. That was
All you had to do was change it to see how badly it was affected.
So those two papers did that experiment, and then we formalized it. That's all I can say.
One question. If you go back one slide. So we face a similar challenge when we try to infer physical properties from a galaxy spectrum, for example.
Right.
But one of the things so you can get this kind of quality in retrieval if, for example, your Mach spectrum is generated using the same models.
I understand.
And fit it. But as soon as, for example, in my line of work, when I switch from when I try to fit a saltpeter IMF generated model, assuming a Chabrier IMF, things get dramatically worse. And so I guess the analog is you're using some sort of synthetic spectral synthesis library. I would reckon there's probably another version of that software. Have you tried inputting someone else's synthetic spectra and retrieving it using your model?
Yeah, so in a sense, this is a trivial test because you generate the model that you then do the inversion on.
It's not trivial because you can get it wrong like you showed before. But
right, and the reason why you get away with it is because this resolution is crappy. But if you do the retrievals on brown dwarf spectra, which on both real and synthetic, on real data and on model grids of other groups, you don't get away with this. In fact, we have done a lot of work on this, and one of the things, if there's time I will talk about it, is that you don't directly measure the gravity of brown dwarfs. It's done from the spectrum, and it's extremely model dependent. And in fact, if you do the retrieval using our forward models, on the model grids of another group, you don't always get the answer they put in unless you're really careful about what you're doing. So it is a problem, and it is a problem that we've worried about for 2 years, in fact. So that was just to convince you that this was a problem and that we thought about it. And now, hopefully you have some confidence in what we are doing. I'm going to show you the application to real data. So I have a very talented student in my group who ran this retrieval procedure through all of the 38 WFC3 transmission spectra in existence. A typical spectrum looks like this, right? So this has 13 data points with that water feature I talked about. And we have moved a little bit beyond just hot Jupiters. So we have 22 Jupiters, 6 Saturns, 4 Neptunes, 2 superbs, and 4 TRAPPIST-1 exoplanets with a rather not so narrow range of equilibrium temperatures. And one of the essential ingredients in doing this interpretation are the opacities or the cross-sections, the cross-section per unit mass. And this gives you a zeroth order idea of where the absorption features are. So these are the absorption features of water in blue, hydrogen cyanide, and ammonia. But it's really hard to get an intuition for this just by staring at the cross-sections, right? So one of the things we had to develop, because out of necessity, was a machine learning method that I talked about briefly this morning called the random forest. So I'll talk about this later in the talk if there's time. But one of the things that the random forest gives you for free is something called the feature importance. So out of the 13 data points in that spectrum I just showed you, you can ask the following question. What is the relative importance of each data point for constraining each of the parameters in the model, right? So for example, out of these 13 data points, I keep saying that there's a water feature at 1.4 microns. And the feature importance tells you that these 2 data points at 4.5 microns contribute 25% of the signal to determining your water abundance. But it's much harder to get an intuition for what the 11 data points are actually doing. And the bluest data points constrain how flat your continuum is, which constrains your gray cloud opacity. This is also intuitive. But the rest of it is not so intuitive to me. Like, for example, the blue, how the bluest data points constrain HCN, and that apparently these 4 data points are really important for temperature. So when we started this thing, I don't trust machine learning methods because I don't like black boxes so much. So we had a competition between human and machine. So my physical intuition versus this procedure. And every time that I was right, it was also right. And every time I was wrong, it was still right. So this is depressing. But allowed me to get more understanding for what each of the data points were doing. So after we had this understanding, I'm going to show you how a typical analysis looks like. I mean, there was... Is that why you were wrong? Because it's really hard to have partial intuitions about I mean, it's just hard for me to look at the cross-section.
Okay, you were guessing.
It's too subtle. I mean, my intuition only works in limits as a theoretician, right? It doesn't work in half limits. I think that's why I was wrong. So I would like to show you a typical analysis. This answers, hopefully, partially your question. So this is a real transmission spectrum from WFC3 of one of the most studied hot Jupiters of all time, HD 189733b. And what my student did was, my student ran this retrieval through a whole hierarchy of models. So there are models that are isothermal, non-isothermal, 1 molecule, 2 molecules, 3 molecules, gray clouds, non-gray clouds, flat line. You get the idea, right? And then what she does for each model is that she calculates something called the Bayesian evidence. And what this means is as follows. Again, I'm using this as a gray box. So from this paper, there's a correspondence between the Bayesian evidence and what the significance in sigma actually is. But what is more important is that you take the ratio of Bayesian evidences of a pair of models. So for example, this is the model of the highest Bayesian evidence, which is the model with gray clouds and water only. And this is the model with water only but non-gray clouds. The so-called Bayes factor, which is the log of the ratio of the Bayesian evidences, is 0.4. And if you look at this table, it means that there is, you can't reject the second model in favor of the first model. Another way of saying it is that all of the green models are consistent with the data. And all of the blue models, there's weak evidence to reject the family of blue models versus the green models. And there's moderate evidence to reject the the model in red, which is a flat line, which is nice because it doesn't look like a flat line. But, well, this doesn't look so flat. But the next example I will show you does look flat. So this is TRAPPIST-1d. This is the transmission spectrum. It suffers from some stellar contamination issues, which I'm not an expert in. But even ignoring these stellar contamination issues, you can see that many models are green, including the one that is a flat line. So since you can't extract any atmospheric compositions from flat lines, I would say that it's inconclusive, the analysis. So on the other extreme end, you have objects like WASP-76b, where many models are rejected. In fact, the purple models are strongly rejected, and there are many models that are purple and red. And the only two models that are green are models that require a non-gray cloud, meaning that these are clouds with particles with radii that are much smaller than the wavelength that is being scattered, so Rayleigh scattering. And this is because there's a spectral, non-flat spectral slope in the near infrared of this spectrum next to the water feature. So our best model with the highest Bayesian evidence would suggest that this is well described by a model with 3 molecules and non-gray clouds. There's a competing interpretation by the group in London, which is that you can completely take out the clouds and add 2 molecules, which are titanium oxide and vanadium oxide. This is motivated by the fact that when you look at M dwarfs, you see evidence of these molecules being present in the atmospheres, and this is used as an analogy to say that they are present in hot Jupiters. So I would say that given the limited wavelength coverage, you can't tell really between these 2 interpretations. And this is one pathological case where you just need a much broader wavelength coverage to tell. So Chloe ran this, I show you 3 examples. Chloe ran this through all 38. She discarded the 8 that were flat lines, and this is what you get, which is not very much, right? So this is the retrieved temperature, not the equilibrium temperature, the actual temperature of the atmosphere that you are sensing. This is the water abundance, which to me looks like a scatter plot. I guess my interpretation of this plot is that planet formation is really complicated. And then when you add atmospheric physics, it becomes even more complicated. Now, if you plot the water abundance not versus temperature, but versus mass, you also get something that looks like a scatter plot. At least I don't see a trend. And the reason why this is significant is because if you follow the literature on retrievals, you will see papers like these, right? Where on the vertical axis is the metallicity, whatever that means. And on the horizontal axis is the mass of the exoplanet. And some of these papers, actually both of these papers, have boldly laid down the metallicity of the solar system as ice and gas giants on top of the retrieved abundances for exoplanets. I would say you should take these plots with well, first of all, we don't find the same result. And the second is you should take these results with a pinch of salt because there are 3 important caveats. The first caveat is that there's no reason that the atmospheric abundance of water should follow the bulk abundance of water in the planet. At least this is not true for Jupiter. And there's the conversion between the water abundance and the oxygen elemental abundance is non-trivial. Most of these papers would assume chemical equilibrium to convert cleanly between one and the other, but there's no reason that these atmospheres should be in chemical equilibrium, at least below 1,000 Kelvin or so. And even if you do this conversion, there's no reason that the elemental abundance of oxygen, which is rather volatile, should follow the elemental abundance ratios of the refractories, like iron or silicon. So it requires that you believe these 3 caveats to believe the conversion between water and elemental abundances in this plot.
Let me ask you another thing. Go back a couple slides. You looked at the scatter and you said, oh, this shows what a difficult problem it is. But you have very noisy data, all the stuff you're working with. So, I mean, can you really conclude that? I mean, suppose the error bars were a factor 10 smaller and all the things you
right?
Wouldn't it, there might be patterns in this that were in fact pretty convincing, even if you maybe couldn't make a model to understand them?
I'm not excluding the fact that when better data comes along, there could be patterns in the data. I'm just saying that given the current quality of the data, you can't conclude there's a pattern.
I don't find that argument.
And as I showed you in the earlier part of the talk, the sizes of these error bars are dominated by the normalization degeneracy.
Right. But at least, as you say, with the far future, with far better data, it doesn't mean that these things will be impossible to draw out of the data.
I agree, but it's curious that you see, like, we are interpreting the same data.
Yeah, I understand where we are now.
Go ahead.
This is my ignorance of planet stuff, of like climate stuff. So from a standpoint of like greenhouse effects and all sorts of stuff like that that might be important to life, what is the difference between an atmosphere that's 1% water and 1 part in 100,000? Like the error bars on the previous plot span, you know, one of them was like 10 to the minus 5, 10 to the minus 2. Does it enter like linearly into these sorts of effects, or like some sort of crazy power that means that those two things are? So
it enters linearly into the opacity, which then sits in a log, as you saw in the earlier part of the talk. So it's a slowly varying function on the transit radius itself, right? Because you're hit by the log and you're hit by the pressure scale height twice, as you described earlier, right? So in transmission spectra, at least, the dependence is slow.
But does that mean, like, for an organism, would I notice a difference on a planet between a fixed composition, everything else, and water changing by 10 to the 2, 10 to the 3?
That depends on what wavelength you're looking at, what temperature it is, which determines what the cross-section of the water is. So because it's not the cross-section or the abundance you're sensing, but the product of the two, right? So other conclusions of the study include, so 35 out of 38 of the WFC3 transmission spectra are explained adequately by a very simple model, which is a model that has an isothermal transit chord with gray clouds and water only. So they're predominantly described by this model. 8 are described by flat lines. None require non-isothermal explanation, consistent with the arguments I made earlier in the talk. There are 2 that are strange and require non-gray clouds, but more data is needed. And cloud composition is completely unconstrained. That's the state of the art. Right, so now if I go back to the same question, I would like to ask the question, what happens when you have ground-based high-resolution spectra, right, which I talked about, I show you an example of this morning. And even from a theoretical point of view, this is interesting, because on one hand, you have high resolution, but you're hit by the fact that you have limited wavelength coverage in some cases. You have a lack of an empirical normalization, because that gets subtracted out when you do the data reduction and calibration. And you have the normalization degeneracy that I told you about. So when you add these, and the fact that the error on each individual data point is very large. So when you add these 5 things together, it's not clear what happens. So this is what a visualization of what the data would look like. This data already exists and has been analyzed by various groups, but this is a model. So the red is an idealized model of a transmission spectra. This is a visible wavelength range. I'm sorry the numbers are not there. This is like 0.4 to 0.7 microns. And the black is the noise model of Hobbs. So each data point is completely dominated by the error, but you can still do cross-correlation to leverage the statistical content of the entire spectrum. But in rare cases where you have strong resonant lines, like sodium in the spectrum, then the signal becomes 2 orders of magnitude stronger, and you return to the regular retrieval regime where retrievals actually work. So this is, as I talked about this morning, this is something that we are actively thinking about, because what I've shown you are retrievals in this regime. But one needs to think about how retrievals work in this regime. And this is where hybrid methods that involve machine learning would be useful. So I see that I still have some time. I would like to show you work that we are currently doing. Please do not put this on social media, because I want my student to get her PhD. And so last year, we published this paper. And you can ask me in Q&A if you want like the details of the paper. But the upshot is that I don't like machine learning methods because they are not only black boxes, but the theory behind these black boxes of, say, deep neural nets are not well understood, right? So for example, I'm not a machine learning expert. I do the machine learning actually with two scientists in the medical faculty at the university hospital who do image recognition to study cancer cells. So they teach us machine learning methods. And they tell me, for example, that the distributions, deep neural nets generate some underlying distribution, but it has never been proven that these things are actually posterior distributions. And yet there are papers in the literature that just use these distributions as posterior distributions. But for a classical method called the random forest, apparently there are papers that have proven that these distributions are posteriors. And a random forest is I wouldn't say it's easy to understand, but it's not the black box that deep neural nets are. It consists of decision trees. Like, for example, you can ask, is this fruit round or elongated? Is it sweet or sour? Is it red or blue? And so on. So you can ask the same thing of spectra. You can actually adapt a decision tree called a regression tree for continuous quantities to analyzing spectra. And when you make many trees and you randomize them using a bootstrapping method, you can then generate the same posterior distributions you would get using, say, the nested sampling method. So we applied this to low-resolution spectra, the Hubble spectra I told you about, which are not terribly interesting. But one of my students is applying this to brown dwarf spectra, which I find much more interesting. So this is an emission spectrum of a benchmark brown dwarf called Gliese 570d. These are the black data points. Sorry, I keep telling her to plot them with bigger points, but she hasn't listened so far. And traditionally, how these data are analyzed is that you would take these model grids, like say, there are grids of brown dwarf models from very established groups, right? So the Sonora grid is the new grid by Mark Marley, who has been doing this for 20-odd years. The Ames grid is at least 15 years old. And we have our own grid called Helios. And these grids don't always agree. And traditionally, how people analyze this spectra is they interpolate the grid onto the data, they calculate a chi-square, and then they, out of the fit comes whatever quantities are in the grid, right? So this is how they do it. And these grids are usually proprietary. You have no access to the codes that are being used to generate them. And it's not clear how to generate posterior distributions from these grids. And the other physics problem is that these grids don't always agree in very important regions. So one discrepancy, which you see here by eye, are the potassium lines at 0.8 microns. And you can see that the agreement between, say, our grid and the other two grids is terrible. And the reason why it's terrible is because it turns out that the detailed shape of the line wings of alkaline metals is an unsolved physics problem. I don't know why. But no one seems to have a first principles way of calculating how pressure broadening works in these kinds of conditions. So one thing that the machine learning procedure gives you for free is something called the feature importance, which I show you for low resolution spectra. Now what you can do is that you can take the random forest machine learning method and you can train it on each of these grids, right? The Marley grid, the Ames grid, and our grid. And you can ask the question, how are these grids constraining the surface gravity of the brown dwarf as a function of wavelength? And you can see it by eye that there are discrepancies where the alkaline metals are, right? So our grid is doing something very different from, say, what the Ames grid is doing. And no surprise, when you apply these three grids to these data points and you extract the surface pressure, the surface gravity values that you retrieve are very different for each of the three grids because of the deficiencies in how you describe the potassium lines. What my physical intuition also doesn't tell me is the fact that even if I drop all of the data that has to do with the potassium lines, that the rest of the spectrum still has some constraining power for constraining the gravity. So this is what we did. I don't have a plot to show you that. But if you just cut out the parts where you have no confidence with what the model is doing, and you do the retrieval using the rest of the wavelength range, we actually now get retrieve gravity values that are consistent across all 3 grids.
Is that a good thing or a bad thing? Sounds like a good thing.
It's a better thing than what people were doing before.
Okay.
So the next thing that is a little better than what people are doing before is that even though I have no access to the codes that generated these grids because these people refuse to make it open source, I can do the following. I can train the grid on, I can train the machine learning method on our grid, and then I can use it to test the other 2 grids. Right? I can ask the question, how well do the grids predict temperature compared to each other? So it turns out that temperature, for reasons I described earlier, because it has an exponential influence on the cross-sections, is very easy to predict. So this is the, I forgot what this is called, the coefficient of determination. So if you get 1, that means it's a perfect prediction. So this is pretty close to 1, right? So these 3 grids give you more or less the same temperature. And the dispersion that you get is due to physics and not due to machine learning. We did convergence tests. But you can see that it does a terrible job at predicting the gravity. And the reason why it's truncated is because these grids are not computed over the entire range that we computed our grids. So this is the other practical problem, that these legacy grids are usually computed over a narrow wavelength, a narrow range of parameter space. And this dispersion is, again, due to physics. It's just due to the fact that it's really hard to get gravities from spectra of brown dwarfs. Now, after I train the machine learning method on the 3 different grids, I can then do retrievals on the benchmark brown dwarf spectrum that I showed you earlier. And these are the 3 different grids and the 3 with posterior distributions on this benchmark brown dwarf. And the nice thing is that they roughly agree. And you understand why the posterior distribution of the temperature is narrow and why that of the gravity is fat, which I described earlier. This is just a calibration factor. It's not important. So at the very least, you can say that we are consistently wrong. It may not be the right answer, but we are consistent. A better thing to do, which I don't have a slide on, is you go to a brown dwarf binary for which you have a dynamical mass. Right? So you have a model-independent measure of the mass. You then make the assumption that the radius is about 1 Jupiter radius, which is supported by empirical trends. You can then calculate the gravity. You can then do the retrieval pretending that you don't know what the value of this gravity is. And we have done this for this object called epsilon Indy A and B. And we get, in one case, we get consistent answers with the dynamical gravity. And in the other case, not, because we understand that the model lacked the cloud physics to describe this object. So everything seems to hang together fairly well. And one thing I love about this is that I can now do these analyses even if these groups are not sharing all of their secrets with me, right? I can analyze the weaknesses in the models. I can analyze the differences in the models. And hopefully, in the long run, this will force all the groups to make their grids and codes public. So the takeaway messages are here. I won't repeat them to you, and I'll just take questions. Thank you. Go ahead.
So in the case where there was a really strong disagreement in the composition of the atmosphere, how much more wavelength coverage would you need to fix that disagreement? Or, I mean, to figure out what's the right answer?
Which one are you talking about? This one?
No, it was before you got to the machine learning.
Here?
No, that. This, yeah. So between those 2 models, how much more wavelength information would you need to be able to determine between those 2 models?
I think if you had a wavelength coverage from 0.4 to 5 microns, which is what NearSpec on the web has, I think that's plenty. You can tell a lot of things apart. I think I mentioned this to some of you when I had conversations. The one thing I learned from this exercise is that observers are very excited about the peaks of spectral lines because that tells you there's a detection. But theoreticians are much more excited about the continuum because the accuracy of my interpretation lies in the shape of the continuum. It tells me a lot. It tells me about clouds. It tells me about pressure broadening. It tells me about collision-induced absorption, and so on. Go ahead.
Can you not combine low dispersion observations with the high dispersion ones? With the low dispersion gives you some normalization, which you can then apply.
Yeah, and this is the question that currently whole conferences are devoted to in my field. But we wanted to ask a different question, which is how much information can I milk out of the high-res spectra alone? And what I talked about this morning was the fact that for a long time, we thought that cross-correlation was the method. But when I talk to my machine learning scientists, they tell me that cross-correlation was the state of the art for image recognition 20 years ago. So this motivated us to look at hybrid methods that can bridge this gap. So this is my focus. Other people are combining the low and the high res. I can show you a mock. I have it in my backup slides. I can show you a mock spectrum of this, what this does.
Do you have a spectrum of that?
So this is a mock spectrum of the sodium doublet at high resolution if I normalize the continuum by the HST value. And the dark posteriors are if I knew what the reference pressure was. Look, it's unconstrained. Right? But if I take away this normalization, it looks like that. So it goes from something quite skinny to that. And unfortunately, the real data looks like that. And this is the real data. So they do some things to the data, which took me a long time to figure it out because I'm not an observer, but it alarmed me when I figured it out. So it turns out that they look at the peaks of these lines around a narrow band, 0.4 angstroms, to confirm the detections. They then measure the continuum around, it's lost in the screen, but they look at broad bands, and they take the average of these broad bands, and they fix the continuum. And then they flatten the continuum, which means they throw away shape information of the lines. And when you do that, you end up with a horrible retrieval. So when you do the retrieval on that, you get 9 orders of magnitude on the sodium lines. So I think this is an example where the observers and theorists need to talk to each other and iterate on this. Because this is horrible. I mean, the information has been erased. The temperature and the abundances are essentially unconstrained. So the high res doesn't actually get you that much.
So when you say they flatten it, what you really mean is they smooth that, they modulate the data rather than divide it by some relation.
You are hitting the edge of my knowledge of what they're doing. So graphically, this is what as far as I can tell, this is what they're doing. But it's best if you read that part of the paper to figure out exactly what it is.
If they take a broad enough band, they'll get the 0 point of the level. But you're saying the shape information actually makes that not reliable, and in fact throws away valuable information. It's not the continuum where they're looking.
I mean, another way of saying it is I would like to see this behavior of the red curve. But what I'm
stay far enough away from that behavior region to do the normalization, then that's your signal.
I guess, yeah. That's what I have to work with.
Can't see anything.
But all the pressure information is contained here.
Yeah, sure.
The interesting stuff is all here, not in the peaks.
But it doesn't look like you have enough signal to noise to see it.
No.
Period.
No, you don't. And you also see structure in the continuum as well. Go ahead.
This might be an unfair question because you may want to learn more than just one thing, but if you could just choose between maximal wavelength coverage or maximal resolution over small wavelength coverage, you would pick?
Maximal wavelength coverage.
Okay. So I think we're in almost exactly the same. So you say you're working far away from what we do, but I don't think that that's true. I mean, I think that that's exactly the same thing in spectral fitting. I think that there's been weird pursuits in getting more resolution or more signal to noise. And I was part of that too. I thought that was the way to go for a long time. But I think even in galaxy SED fitting, broad baselines of the continuum is super important. That's really it. And the more you sample the continuum, the more you can make up for the fact that you don't actually have information on all of the line details. It's interesting that that's the same at such different scales.
Right. I mean, it comes down to the basic radiative transfer physics, right? I mean, like scattering theory, if you want to know whether it's a large or small particle, you read that in the continuum, in the shape of the continuum. It's encoded in the continuum. I was having a conversation with you earlier about, I'm one of the non-voting members of LUVOIR, and I'm a bit alarmed. I joined late. I'm alarmed that the wavelength coverage is 0.5 to 2 microns. So they've opted to go for a very big mirror and a very narrow wavelength coverage. I would have gone for a much broader wavelength coverage because of the reasons we just talked about.
Yeah, but they can't afford to build a cryo telescope of that size, and that's what caused JWST practically its existence.
Right.
So they can't go to 5 microns or 10 because it's just would be already it's a $10 billion, $15 billion project.
Yeah, I understand.
So I'm sure they would appreciate your desire, but it's just.
I mean, I worry about the fact that when you're restricting yourself to 0.5 to 2, you're looking for, you basically have a preconceived notion of what you're looking for.
So you're saying, given that all this money is being spent to detect signatures of life on terrestrial-like planets, it wouldn't be great if it turns out that even after you've done that, you're completely uncertain about what you found. And I appreciate that. So maybe you have to be, instead of arguing that you could only go to 2 microns, you have to go to 5 microns. You have to argue that this is not the mission should be built.
I mean, you have 2 sets of problems. The first set is that you have the spectrum in whatever resolution or signal to noise, and then you just want to ask, is there water, is there CO, is there CO2, and how much, right? And I think I've convinced you that that's not a straightforward question to answer. And then even after you get that, you want to answer the question, how can I rule out that this is entirely abiotic? And that's also a very tough question. And I would say the answers to both these questions are helped by wavelength coverage, by sampling more of the continuum. That would be my opinion, that most people would not agree with.
You said that the line broadening was an unsolved problem. Is there no laboratory experiments that have been done to solve that problem empirically?
For the sodium line, the last study on it was in 2012 by a French group, as far as I can tell. For the water lines, there's a group at London, UC London, led by Jonathan Tennyson, who got a €2.5 million grant to just work on water lines. So the pressure broadening of water lines is very, very well understood by now. But there's a lack of motivation to do the same for the other molecules. And in fact, one of the things that surprised me was when we were doing the cross-correlation of the atomic lines for these really hot objects, and we go to these databases, the Caruso database, there's no information for pressure broadening, 0, nothing. So you just get line peaks. You essentially don't have any information about line wings at all. I do not know why.
Can I go back to the JWST, the LUVOIR question? When you've heard discussions of this, have people discussed, particularly, for example, going to 5 microns or what the temperature of the telescope would have to be in order to be background limited? Maybe you can go to 5 microns. I mean, JWST goes far redder than that, and therefore it has to be 50 degrees Kelvin. So has there been that discussion? I sort of on the advisory group too. I never heard anything like that.
In LUVOIR, you were saying?
Yeah.
I joined rather late, so by the time I joined, the wavelength range had been settled. I'm sure they had these conversations, but they had them without me.
Well, it's an interesting piece of information that needs to make it to the decadal survey because there are going to have to be choices between that and HABEX, as you said, and the other one. So maybe that step, which is really an ultimate step in terms of cost difficulty, is a step too far if these are the irreducible problems that you can encounter if you only have data that is of a narrow wavelength range. It's very important.
I mean, it depends on what your question is. If your question is to take spectra of Earth analogs, I think that's fine, right? But if you want to detect things that are a little bit different from Earth analogs, then what we are talking about is relevant.
Well, explain that. You mean, let's just say it's terrestrial planets. They could be super Earths. I mean, when you say you don't think people are just after Earth size, same conditions as what do you mean? Suppose you accept that we're going to have smaller things, Mars analogs to super Earths. You want to look at the whole range. Could you at least distinguish with that kind of?
I would say there are two types of people interested in habitability in my community. The first camp believes that the interesting planets have 70% nitrogen, 20% oxygen, water, and carbon dioxide.
Yeah.
And the second camp, which I belong to, thinks that we should just look. We should just look, we should just do the retrievals to the best of our ability, we should collect an inventory of all of these things, and we should just think about it. That would be, meaning you should do a very intelligent fishing expedition.
Yeah, I'm on your side.
So you don't think we're in the follow-up stage quite yet? We should be doing more stamp collecting.
No, I think we should fully do follow-up. I just don't think we should follow up on a specific type of object that fits our preconceived notions of what habitability actually is.
Alex, do you have one question?
Yeah. Just about the point of random forest, is there a reason that that is better than something like even simpler, like polynomial interpolation between the models?
One of the advantages of the random forest method is the fact that suppose I had a 10 parameters in the model, so I have a 10-dimensional space to sample. If you wanted to do interpolation, I imagine that that space would have to be an evenly spaced 10-dimensional grid. Whereas in the random forest, you don't need to do that. You can sample randomly in this 10-dimensional space, and you can sample in a very sparse sense. In fact, the relationship between the dimensionality of the grid and the number of points you have to sample is quite gentle. That's one practical advantage to using the random forest, as far as I can tell.
Okay, any more questions? You can come and ask Kevin after stop. Thanks very much.
Thank you.
And if you're interested in going to dinner, let me know. We'll meet in the lobby at 5:45.
The origins, the third of those missions, the origins.